Hi everyone, this is Aaron Carmen from AXE Electronic back with another video on our series covering basic circuit analysis. So previously we've talked about Kirchhoff's laws, we've talked about resistors in series and resistors in parallel. So just for a little bit of review before we get started on this one, we're going to review what we mean by resistors in series and resistors in parallel. So the first thing is we're going to say resistors in series. If we have two resistors connected like this, like we have here, this is the exact same thing as, well, here, before we get onto that, let's call this one R1 and this one R2. So R1 and R2 are in series. This can be modeled as just a single resistor whose value is R1 plus R2. Okay, so this is a series resistor, and this is the equivalent resistance, R1 plus R2. Okay, so if we have these two resistors in series, we can simplify it to be R1 plus R2. Okay. Now, if we have two resistors that look something like this, so they have two resistors, these are in parallel, this is R1, this is R2, okay, then we said that we can, again, change this into just another single resistor, and the simplified formula that we came up with was R1 times R2 over R1 plus R2. Okay. Now, if you don't know how we got to that formula, then I suggest you go back and watch my video on parallel resistors. I'll explain to you how we got that formula and give you a couple of examples with that. But this is the simplified formula, and this is the one that you're going to want to remember whenever we're doing these problems. So for this video today, I've got 5 different problems. They're fairly simple. They're not going to be too very complex, and we're going to walk through each one of those. And I'm going to talk while I do them. I don't have the answers in front of me, so you're going to be hearing me and seeing me work these out fresh. No answers. I don't know any specific way to do it, so you're going to see how I, as an engineering student, work these problems out and how I arrive at these answers. Okay, so let's start with this first one, number 1. Scroll down a little more. So for number 1, we have a 5-volt voltage source, 2 resistors whose values are 2 ohms and 1 ohm. Okay, so in order for us to completely solve this circuit, we want to know the voltage across each of these resistors. So I'll do plus and minus. Do plus and minus. Call this one V1, plus and minus V2. And then we want to know the current flowing through every component or flowing through every branch. So there's only one current here, which is, we can just call I. Let me do a lowercase I. Okay. So what's our first move here? Well, our first move is that we can see that these two resistors, let me switch to red pin, these two resistors here are in series. Okay, there's no branch between the two. Okay, so those two resistors are in series. So what we can do is that we can model this as just our 5-volt source. Let me scoot over, zoom out and scoot over a little bit. So what we can do is we can model this as our 5-volt source, and then a single resistor whose value is the sum of those two resistances. So value is 3 ohms. Get rid of that math, we can just put 3 ohms here. Okay, so now this is just a simple Ohm's law problem. If I want to know the current flowing through here, I, Ohm's law tells us I is V divided by R, so that's going to be 5 volts divided by 3 ohms, okay, and that'll give us 5 over 3 amps, or 1.67 amps. Okay, so you can keep it in fraction form or you can do decimal form, whichever one's easiest for you. If it was a final answer, I'd probably stick with 5 over 3, but I'll probably stick with 5 over 3 right now since I don't have a calculator right here in front of me. Okay, so now that we know this current, we can go through and we can solve for the voltage at each of these. So once again, Ohm's law says V is equal to I times R. Okay? So if we want to know V1, that's going to be I times 2 ohms. That's a terrible looking omega. So we're going to call that I times 2 ohms, and that's going to be equal to, we'll keep it as 5/3 times 2 ohms. Okay, and that's going to be equal to 10 divided by 3 volts. Okay, and that's also 3.33 volts. All right, and then we'll just repeat that process for V2. V2 is going to be I times 1 ohm. Okay, so that's going to be 5 divided by 3 amps times 1 ohm, or 5 divided by 3 volts, which is 1.67 volts. Okay. So now let's rewrite this circuit. We have 5-volt source. Okay, and we have this resistance, and then we go back to the source. This is 2 ohms and 1 ohm. All right. We already said the current, I'm just going to put it down here, the current is 1.67 amps. The voltage across this 1 ohm resistor is 1.67 volts. The voltage across this 2 ohm resistor is 3.33 volts. Okay. So let's do a couple of checks and make sure that this question or this answer makes sense. So first thing is going to be KVL. Okay. KVL says the sum of the voltage rises and drops around a closed loop has to be equal to 0. Okay? So if we start down here, let's say this bottom left corner, we rise by 5 volts, okay, and then drop by 3.3 volts, drop by 1.67 volts, and get us back to the beginning. So 5 minus 3.33 minus 1.67 is 0, so KVL is satisfied. So KVL is satisfied. KCL, okay. KCL, there's no branching nodes in here. There's only a single current, so KCL is already satisfied. We don't have to really do any checks on that, not for this one. Okay, so now we can say this circuit is solved. KVL is satisfied, KCL is satisfied, and we have the current and voltage across every component here. Okay, so that's number 1. So that was pretty easy. Don't think all of them are going to be this easy. They're going to get a little bit harder as we keep going, but now we can move on to number 2. So number 2. This time we have a 20-volt source. Okay? And then we have one resistor here. This is a 10 ohm resistor. Then we have another resistor over here. This is a 5 ohm resistor. All right? So now, like we said before, we need to know the voltages and the currents across every component here. Okay, well, first thing that I can see is we have this closed loop here, okay, and then we have, well, let me get rid of that. So we have that first closed loop, and then we have the second closed loop around the outside. Okay, so what that tells me is that the sum of the voltage rises and drops, that that's KVL, the sum of the voltage rises and drops across every closed loop has to be equal to 0. So that tells me that, that tells me that we know V1 here is, let me get rid of that. We know here that this voltage is going to be 20 volts. We know here that this voltage is also going to be 20 volts. Okay, so now we know the voltage and the resistance. We can figure out the current. So let's call this I1, call this one I2. So I can say I1 is equal to 20 volts divided by 10 ohms. It's equal to 2 amps. Okay, so I1 is 2 amps. Do the same thing for I2. It'll be 20 volts divided by 5 ohms. Okay? And that's going to be equal to, 4 amps. Alrighty. So now we have these two currents, all right, and we can say, all right, what is this current? I'll call this one I3. So we have I3 going into this node here, I1 leaving, and I2 leaving. Okay? So Kirchhoff's current law says I3, the current into the node, has to be equal to the sum of all the currents leaving the node, I1 plus I2. So that means that I3 is going to be just 6 amps. Okay, so now we know the current through every component, the voltage across every component, and so this circuit is pretty much satisfied. Okay, and notice I managed to solve this circuit without having to do the parallel resistor combination that we had talked about before. So you might be wondering, why is it that we didn't have to do the parallel resistor combination? Well, the answer is we were able to just simplify it enough. So I'm gonna take another crack at this problem, except this time I'm just going to simplify the parallel resistors. Okay, so what I'm going to do here is, let's move down. I'll use the green color this time. So we have our 20 volt source. our 10 ohm resistor, and a 5 ohm resistor. Okay? So what we can do is we can say these two resistors are in parallel, because they are. They're in parallel. They have the same beginning and the same end. Okay? So what we can do is we can say, let's simplify this. So let's say we have our 20 volt source. We're going to try and simplify this into just a single resistor. Okay? So this resistor is going to be equal to 10 times 5 over 10 plus 5. It's 50 divided by 15 ohms. Okay? We can simplify this a little more. This is going to be 10 divided by 3 ohms, which is equal to 3.33 ohms. Okay? So now we know the resistance, or the equivalent resistance here. We know the voltage across it is 20 volts. We can calculate the current. So I'm going to use the blue here. The current, I, is going to be equal to the voltage, 20 volts, divided by the resistance, 3.33 ohms, which, voila, is 6 amps. Okay? So now we can rewrite this circuit down here. So we have our 10 ohm resistor, a 5 ohm resistor, 20 volt source. And now we know that we have 6 amps. That's a terrible looking 6. We have 6 amps coming out of the source, and it's being split amongst these two. So we have I1 and I2. Okay? So now what we can do is we can say, okay, well, let's look at here and try and make sense out of this. We have 6 amps coming in, okay? And then we have twice as much resistance in this branch as we do, or in this left branch, as we do in the right branch. So that means that twice as much current is going to flow through the right branch because it has half as much resistance. Okay? And then we can use this to further solve, and that arrives at the same conclusion that we have 2 amps coming through this branch and then 4 amps through the second branch. Okay? So this one was a little more convoluted, a little bit of a longer method of doing this. I think that personally, I think that the best way to do this would be to identify that you have 20 volts across both of these resistors, and then use that to solve and get all the voltages and currents. But if it helps you to do it this way, then by all means do it this way. Or if you only need to know the total current coming out of the battery, then the source, and this is the best way to do it. All right, so now let's move on to number 3. So number 3. Now remember, I said these were going to get a little more complicated. Okay, so what we have now is we have a 20 volt source, a 5 ohm resistor in series with this source, and then we have a split. We have a split between a 10 ohm resistor and another 10 ohm resistor. Okay, so how can we go about solving this problem? Okay, well, we can't do the shortcut that we did in number 2, where we just say, oh, they have the same voltage drop across those 10 ohm resistors, because, well, there's a little bit of a voltage drop across this 5 volts, so we can't just immediately arrive at some conclusion. Okay, so what we're going to do is that we're going to have to take this just one bite at a time and identify something that we can simplify in order to make this problem more solvable. So the first thing that I see is that we have these 2 resistors in parallel. Okay, so what we can do is we can take one step, turn this circuit into 20 volt source, 5 ohm resistor coming out of the source, and then an equivalent resistance for those 2 resistors in parallel. That equivalent resistance is 10 ohms times 10 ohms over 10 ohms plus 10 ohms, which gives you a resistance of 5 ohms. Okay? So now we have 5 ohms and 5 ohms. What you can see is that these two are in series. These 2 resistors here are in series. So what we can do is we can take this a step further. I'll go down here and say 20 volt source. And now we just have, oh goodness, that's a bad looking resistor. Now we have just a single resistor. Okay? Now we have 5 ohm resistor in series with a 5 ohm resistor. That's going to give us 5 ohms plus 5 ohms, 10 ohms. Okay, so now we have a 20 volt source and just a 10 ohm resistor. And we can use this, to solve the current coming out of the battery, I. I is equal to the voltage, 20 volts, divided by the resistance, 10 ohms, 2 amps. All right, so we know that there's 2 amps coming out of that source. All right, so now let's take this information and let's go back up here and work on it a little bit. Okay, so let's go back up to this. Well, I'll just draw a new one. So let's undo our work a little bit. Okay, so we have this 20 volt source, a 5 ohm resistor in series with the source, and then 2 10 ohm resistors in parallel. Okay. Now we found out there's 2 amps coming out of here. Okay, so there's nowhere for this current to go except through this 5 ohm resistor, so that means we know the current in this 5 ohm resistor is 2 amps. So we can solve, well, I'll use the green color here. We can solve, we'll call that V1. V1 is going to be equal to I times R. That's going to be 2 amps times 5 ohms, 10 volts. Okay, so that means we have, I'll erase that V1, we have a 10 volt drop across that resistor. Okay, so now let's start down here. We go up, have a 20 volt increase, and then we have a 10 volt drop. Okay, so we started off at 0 volts plus 20, so this is 20 volts up here. And then that means over here we have 10 volts after we have that drop. Okay, so we have 10 volts here, 0 volts here. Now we know the voltage across both of those parallel resistors. Okay, so we don't even have to do the parallel simplification. Okay, all we have to do is we can say, let me use the green again. I'll call this one V2 and this one V3. Okay, and then let's see, I'll use this, or I'll use red for current. Call this one I1 and I2. Oh, I'll do it with it. So I'll call this one I2, call this one I3. Okay, so now we just have to do Ohm's law. So I2 is equal to V2 divided by 10 ohms. Okay, we know V2 is 10 volts, so 10 volts divided by 10 ohms gives us 1 amp. Okay, so I2 is 1 amp. Okay, and we can repeat that calculation for I3. I'm not going to do it here. You can do it on yourself if you want to verify it, but we also get 1 amp here. All right, so now we think we've solved this circuit. Okay, but let's sanity check our numbers real quick. So first thing, let's do KVL. Okay, so first let's look at this inner loop. Okay, so we have the 20 volt source, 5 ohm resistor, and this left 10 ohm resistor. Okay, so if we again start from the bottom here, start from this bottom, 0 volts, go up, we rise 20 volts, so we rise 20 volts, drop 10 volts, and then V2, let's see, V2 we said it was 10 volts, so we drop here to 0 volts. Okay, so this inner loop is satisfied. Now if we do the same thing to the outer loop, we're going to find that it's also satisfied, so KVL is satisfied. All right, that's our first hint that we're doing this right. Second thing we need to make sure, KCL, so I'll use KCL, red, because it's current. Okay, so here is the only branch, that red dot. Okay, well, there's 2 branches technically, but we'll look at this first one first. So we have 2 amps coming in, 1 amp leaving here, 1 amp leaving here. So notice we have 2 amps coming in, 2 amps total leaving. Okay, so this node is satisfied. Down here, okay, we have 2 amps leaving because it has to return to the battery, 1 amp in, and another 1 amp in. Okay, so we have 2 amps in, 2 amps out. KCL is satisfied. KVL is satisfied. KCL is satisfied. We've solved this circuit. Okay, so this one you can see it was a little bit more challenging, but all it is, it's just reapply what you know. So you can you reapply parallel series resistors to calculate whatever it is that you need to calculate, and then just take things one step at a time. No matter how complex the circuit is, you're always going to be able to just take things one step at a time and figure it out. Okay? So let's keep on going. Keep on going. I said I had 5 for you, and right now we've only done 3. So let's take a peek at number 4. Number 4, we have 12 volt source. Then we have an 8 ohm resistor. Okay, an 8 ohm resistor. And then here we have one branch with 2 resistances in series. And those resistance values are 6 ohms and 12 ohms. Okay? And then we have a second branch with just a single 6 ohm resistor. Okay, so how can we solve this? You might be asking yourself. Well, that's a great question, and I'm going to tell you how. So the first thing you can do, like I said, just find one thing that you can simplify. That's all these problems are, is just simplify, simplify, simplify until eventually you get your answer. Okay, so the first thing I can see is that these 2 resistors are in series. Okay, so let's start by simplifying that. So what we can do is we can rewrite this to be, write it a little smaller this time. Our source is that 8 ohm resistor here. We're going to simplify that into a single resistor and then 6 ohms here. Let me have that written down. 12 volt source. All right, so now what is the value of this, or this resistance right here? Well, we're taking 2 resistors in series, so that means we're going to add up their resistances. Skip the math just to keep it concise. It's 18 ohms. Okay? So that's one step that we've taken. Next step. Is there anything you can see that needs to be done? Hopefully you're shouting at your screen right now. There's 2 resistors in parallel. We know how to simplify those. Whoop. Guess I hit undo too many times. So we can simplify those 2, and it'll become 12 volt source, 8 ohm resistor, and then those 2 parallel resistances are going to become just one single resistance. All right, I'm going to rewrite this formula just so you can get it nailed into your head. 18 ohms times 6 ohms. Let me scroll up that way you can see exactly what it is that I'm doing here. So 18 ohms times 6 ohms over 18 ohms plus 6 ohms. Okay, so this one, probably going to need a calculator for. I know I'm at least going to verify it with a calculator. So 18 times 6 is 108. Divide that by 24, gives you 4.5 ohms. Okay, so now, what do we have here? We have these 2 resistors in series, so that tells us we can simplify those even more. So last thing we're left with is, I'll make it a little bigger. Last thing we're left with is 12 volt source and a single lonesome resistor. Okay, and that resistor is going to be the sum of the 2 resistances in series, 12.5 ohms. Okay, so like I've said before, I have not seen the answers to these, so my apologies for not making these numbers all nice and round. But this is going to get a little messy. I'm going to keep it in decimal notation because now I've got my calculator out. Okay, so first thing is, let's figure out what is this current here. We'll call it I1. So I1, Ohm's law is just V divided by R, so that's going to be 12 volts divided by 12.5 ohms. And if we plug that in, that gives us 0.96 amps. All right? So 0.96 amps coming out of that source. Okay, so now what we can do is we can go back up to this first problem. Go back up to this first image. We say we have 0.96 amps coming out of this battery, or coming out of this source, sorry. So first thing we can figure out is, what is V1, the voltage drop across this first resistor? Well, V1 is going to be I1 times R, so that's going to be 0.96 times 8, so I'll do 0.96 times 8, gives me 7.68 volts. So we have 7.68 volts across that. Okay, 7.68 volts. Now, what we can do is we can, again, start here. I'll call this 0 volts. we have a 12 volt rise and a 7.68 volt drop. So if we do 12 minus 7.68, we're left with 4.32 volts here. Okay, so 4.32 volts. First thing we can do is we can calculate, well, let's see, we know the voltage here, we know the voltage here, and the voltage here is 0 volts. Okay, and now we can use that to solve for this current. Call that I3. So I3 is going to be equal to the voltage, 4.32 volts, divided by the resistance, which is 6 ohms here. Okay. And that will be 4.32 divided by 6. Oh, divided times 6. 4.32 divided by 6. That'll give us 0.72 amps. Okay, so I3 is 0.72 amps. Okay. So what do we do about this whole mess right here? Okay, it's a little more complicated, but we can separate it out. Okay. So the first thing we can do is we said, all right, well, let me move over to here because it might be a little easier to see here. We have 0.72 amps coming through here, 0.96 amps, and then a 7.68 volt drop across that resistor. Okay, and we know this is, well, I'll move it down here. We know this is 4.32 volts. We know this is also 4.32 volts. Getting a little crowded, but we still have enough room to do what we need to do. So what you'll notice is that I moved it over here because it's a whole lot simpler, because we have voltage, we have resistance, so we can just use Ohm's law. 4.32 volts divided by 18 ohms gives us 0.24 amps. I didn't, let me clear that up a little bit, 0.24 amps. Okay. Now I didn't write that equation, but it's just Ohm's law here, so you should be able to work that out on your own. And then we can, let's say, move back over here. So we know that for both of those resistors, there's 0.24 amps going through them. Okay? So we need to figure out, the last thing we need to figure out is the voltage drop across each of these. Okay? So how do you figure out voltage if you know the current and resistance? Ohm's law. So voltage is equal to current times resistance. Current is 0.24. For this first one, the resistance is 6, so we'll call this 1.44 volts. I'll go ahead and erase this red line here and move it, let's say, to the other side. So let's say 0.24 amps. And this first one is 1.44 volts. Now the drop across the 12 ohm resistor is going to be that same 0.24 amps times 12 ohms, 2.88 volts. Okay, so let's fully notate this thing. So we'll call this 4.32 volts. Okay, 4.32 volts. Okay, now we think we have this circuit solved, but what do we have to do? We have to check everything. So let me write our KVL and KCL. Let's start off with KCL because that's a little bit simpler. Here at this node, we have 0.96 volts going in, and then 0.72 amps going out, 0.24 amps going out. 0.24 plus 0.72 gives us 0.96. So KCL is good at that node. What about this bottom node? We have that same 0.24 amps going in, same 0.72 amps coming in, and then the same 0.96 amps going out. Okay, so similarly, KCL is solved here, so KCL is satisfied for this circuit. Now let's check KVL. So let's look at this inner loop first. So this inner loop, we have a 12 volt rise, okay, minus 7.68 volts across the 8 ohm resistor. Okay, so we're going through this inner loop, so that means we're going to be taking the 6 ohm and 12 ohm path. So if we do minus the voltage drop across the 6 ohm resistor, minus 1.44, okay, and then minus the voltage drop across the 12 ohm resistor, so minus 2.88, that gives us 0 volts, which is exactly what we wanted. So that's telling us KVL is satisfied. Well, no, that was a little bit too late. KVL is satisfied for the inner loop. Now we have to check the outer loop. So the outer loop, we still have that same 12 volt rise, minus 7.68 volts from the 8 ohm resistor, and then minus that 6 ohm resistor on the outside minus 4.32 volts, voila, gives us 0 once again. So KVL is satisfied for this circuit. So now we have completely solved this circuit. We know the voltage and the current at every single position on the circuit. That's good enough for us, and as well it should be. This thing is completely and entirely solved. All right, the last problem. And this one's going to be a doozy. I'll try and work it out as best as I can and in as much detail as I can, just to make sure that you have a completely solid understanding of what I'm doing on this one. So this is going to be the one you stick around for. So we start off with 16 volt source. Okay, 16 volt source. First thing, 2 ohm resistor. Okay. Then start off a branch, 10 ohm resistor. Let me scroll down on my notes here so I can make sure I'm getting everything. 10 ohm resistor. Now we have another branch with a 10 ohm resistor and a 20 ohm resistor. Okay, that's connected down here, and then that'll be one route. Okay, so after this we can move over here. We'll have a 6 ohm resistor. Scoot it down a little bit more, and this will be 4 ohm resistor. Okay, so definitely the most complex circuit we've done so far. But like I said, everything is just going to be take it one step at a time, simplify one thing, and then before you know it, you'll discover something new. You might find a current coming out of the battery, and that'll let you know the voltage drop, yada, yada, yada. So let's go ahead and get our hands dirty, and we can see what's happening here. Okay, so the first thing, well, I'm going to do two things at once. First thing I notice is that there are these parallel resistors here. Okay? And then there's also these series resistors here. Okay? So series and parallel resistors, we know how to simplify. So let's go ahead and do it. Okay, so I'll come down here, and we'll take one step, 16 volt source, 2 ohm resistor coming out of that source. Okay, then here we have our 10 ohm resistor. And then now we're going to turn those parallel resistors into just a single resistor. And we're going to turn those series resistors over there into a single resistor. Now, series resistors are definitely easier. So this is going to equate to 10 ohms. 6 ohms plus 4 ohms will give us 10 ohms. So this is a 10 ohm resistance here. Okay, now, this one's a little bit trickier. So I'm going to, let me go ahead and make the notes here. So we have 6 ohms plus 4 ohms. That's what gives us 10 ohms. For this one over here, let's talk about it a little bit. So remember the formula I told you. It's 20 ohms times 10 ohms over 20 ohms plus 10 ohms. Okay, that's the parallel resistance formula that you're going to need to memorize. Okay, because this is something that you can remember very quickly. It's something you're going to use a lot. I mean, I have used it a countless number of times throughout my time in college, so it is definitely an important formula to know, and it is very beneficial if you know it like the back of your hand. Okay, so what we can do is we can say this is 200 ohms squared, because we have to square those 2 ohms. Okay, 200 ohms squared divided by 30 ohms. Okay, and that's going to leave us with, let me go ahead and do the math to make sure I'm doing this correctly. 200 divided by 30. It's going to give us 6.67. Oh gosh, we're not talking about current. That's going to be, 200 divided by 30. That's going to give us 6.67 ohms. See, sometimes these things just, sometimes they get a little bit hectic. But you just have to make sure you're sanity checking yourself. And you'll make mistakes, but as long as you're sanity checking yourself, you'll make sure you're doing the right thing. So this is a 6.67 ohms. All right. So now, next step. Got this whole shebang. Those are just series resistors. Remember, if we have 2 resistors in series, we can just add their resistances together. So now what we have is 16 volt source, 2 ohm resistance, that equivalent series resistance, and then that was 10 ohms. 10 ohms here, and then 10 ohms plus 16.67 or 6.67 ohms, sorry, will give us 16.67 ohms. All right, next step. I have this whole number. Okay, so this is going to be parallel resistors. So that's going to give us 16 volts, 2 ohm resistor, and then now we're going to have just a single resistor in place of those parallel resistors. Okay, so I'll write the formula out again. Let me do the general formula. R1 times R2 over R1 plus R2. So that's going to give us 16.67 times 10 over 16.67 plus 10. Now, I don't care how good at math you are, it's probably good to whip out a calculator for this one. So 16.67 times 10 divided by, okay, we can do that, 26.67. Okay. And that's going to give us 6.25 ohms. All right, so 16.67 in parallel with a 10 ohm resistor will give us 6.25 ohms. See, I told you some of these weren't going to be that nice of numbers. All right, and then the last thing is that we have 2 resistors in series. So this is just 16 volt source. What do we do with series resistors? We add them together. So this is going to be just 8.25 ohms. Make sure you can tell that's 16. Okay. So now we know the equivalent resistance that the source sees. So if we want to find the current, all we have to do is we do Ohm's law, which is V equals I times R, or current is equal to voltage divided by resistance. So if we want to know the current, that'll be I is equal to 16 volts divided by 8.25 ohms. 16 divided by 8.25 will give us 1.94 amps. Yeah, 1.94 amps. It's a little bit not as clean of a number, but it's approximation. 10% rule. The good thing in engineering is you can approximate a little bit. So 1.94 amps. So now I'm going to rewrite this circuit from the very beginning. Okay, so that's way too big. I don't want to take up all the space. So plus minus 16 volts, 2 ohm resistor. Okay. Oh, I forgot it's a little more complicated than that now. All right, so this is the circuit that we started with, and this is 10 ohms, 20 ohms, 10 ohms, 4 ohms, and 6 ohms. Okay? So, what do we now know after doing all of that? Well, we know the current coming out of here is 1.94 amps. Okay? 1.94 amps. So if we have 1.94 amps going through a 2 ohm resistor, well, we know the current, we know the resistance, we can figure out the voltage. So Ohm's law, V equals I times R. I is 1.94, R is 2, so 1.94 times 2 will give us 3.88 volts across that resistor. Okay. So this is the notation I like to use again. So we have 0 volts here, 16 volts at the top. All right, and then if we do 16 volts minus 3.88 volts, that'll be 12.12 volts here. Okay, so the next step is going to be, well, there's nothing that we can really do with this right now because we have, this whole mess here that's, not simplified. We have this here that's not simplified. Okay? So we're going to have to simplify something if we were going to figure out, the current or the voltage across any of these. So first thing, probably easiest to simplify, is going to be this right here. Okay, so I'm just going to go ahead and erase it right here for now. Okay, we can call this just a 10 ohm resistor, okay, because we have a 6 ohm resistor and a 4 ohm resistor in series. That's the same thing as a single 10 ohm resistor. And if we have 12.2 or 12.2 volts, this is volts here, 12.2 volts, this is 0 volts down here at the bottom. So the potential difference across that series resistor is 12.2 volts. Okay, now we know the equivalent resistance, we can figure out the current. So Ohm's law, once again, Ohm's law if we want to know the current, it's voltage, 12.12, divided by our resistance, which is 10. So that tells us that there is 1.21, I'll just call it 1.21 for now, 1.21 amps, okay, going into this node here. All right, so I'm going to backstep a little bit now. I'm going to backstep. We replaced, remember, that 6 ohm and 4 ohm resistor with a single 10 ohm resistor. And that allowed us to find the current going through this branch. Okay, so now that we found the current, we can put that 6 ohm and 4 ohm back the way it was. And what we can do is we can say, all right, what is going to be the voltage across each of these? Well, we know the current, we know each one's resistance, so now we can tell you the voltage. Okay, so if we have, remember, Ohm's law, V is equal to I times R. I is 1.21. For this first one, R is going to be 6 ohms, so we can say there's 7.26 volts across that 6 ohm resistor. We do the same thing for the 4 ohm, 1.21 times 4 gives us 4.84 volts. Okay? So let me sanity check these numbers real quick. 4.84 plus 7.26 gives us 12.1, okay, which is a good enough approximation because, we were already approximating. So 12.1, 12.12, that's a gimme, okay? You're pretty close to it, all right? Now, like I said, if there's a little bit of a rule, if you're, within reason, close to it, and, if it's a rounding error, then by all means, you're probably along the right track. But if you're, tenths or, volts off, then that's probably it's probably not the best practice. But anyways, this is just a rounding error, and we were rounding anyways. Okay, so now we know the voltage across those two resistors and the current through each of them. How can we handle this whole mess here in the center? Okay, so we're going to have to follow a similar method of just simplifying it. And fortunately, we already sort of simplified it up here. So if we look back up here at the start, we had this whole mess. First step we did was we simplified the parallel resistors, okay, and turned it into this here. And then we simplified it even further to turn it into just a single resistor. Okay, so we managed to represent all of this as a single 16.67 ohm resistor. Okay, so that's what we're going to do here. I'm just going to erase it for right now. And we can say, all right, so we're going to represent this as a single 16.67 ohm resistor. 16.67 ohms. Now, if I were to give you that and asked you, what's the current? Okay. If you want to know that current I, again, it's just Ohm's law. I is going to be equal to 12.12 volts divided by 16.67 ohms. So 12.12 divided by 16.67 gives us 0.73 amps. Okay, so let me erase that I, and this is 0.73 amps. Okay, so we found the current. Let's go back to the way it was before. So before we had a 10 ohm resistor in this branch where it was a 20 ohm, 10 ohm, and 10 ohm. Okay, let's start off by calculating the voltage drop on that 10 ohm resistor because we know the current, we know the resistance, so we can say the voltage drop is going to be current 0.73 times the resistance, which is 10, so it is going to have a 7.3 volt drop. Okay. Now we have 12.2 volts and then a 7.3 volt drop. So if I do 12.12 minus 7.3, that tells us there's 4.82 volts here. We know that this is 0 volts down here at the bottom. This is 0 volts here. So now we can calculate the current through each of those two resistors because we know for each of these there's going to be a 4.82 volt drop. Let me move that a little bit further out of the way. Oh, okay, well, never mind. 20 ohms, and then this is a 4.82 volt drop. Oh, gosh. Okay, so 4.82 volts across both of those. We need to figure out the current. Okay? So the current is going to be the potential difference, which for both of these is 4.82, divided by the resistance. So 4.82, we'll start with the 20 ohm, divided by 20, gives us 0.24 amps. Okay, now for the second one, 4.82 divided by 10, that's going to give us 0.48. Let's see, 4.82 divided by 20. Okay. Well, I can already tell you we're going to have a little bit of a rounding error at the end, but it's okay. All right. So now we think we have this thing completely solved. We know the current, we know the voltage at every single component here. So last thing we always do, check our results against KVL and KCL. So we're going to start with KCL. So the first node I want to start at is here. We have 1.94 amps in, 0.73 amps out, and 1.21 amps out. So 1.21 plus 0.73 gives 1.94. So the current in equals the current out. We're good there. What about this node here? So at that node, we have 0.73 amps in, 0.24 amps out, and 0.48 amps out. That's an amp there. So 0.24 plus 0.48 gives us 0.72. Okay, so we have 0.72 amps coming out and 0.73 amps coming in. Now, if you were doing this for an exam or anything like that, yes, by all means, carry out as many decimal places as you want to. But since I wanted to keep this sort of simple and I didn't want to have to write out so many different decimal places, I had to do some rounding. So this is a rounding error, but KCL is satisfied for this node. Okay. Now, similarly, we're going to have here this 0.73 amps coming out. Okay. Again, this is due to the rounding error because all the current going into this little section here has to come out. Okay. And similarly, 0.24 amps plus 0.48 amps gives us 0.72 amps, but like I said, it's a rounding error. So next, let's check this node here. So like I said, we have this 0.73 amps coming in from those parallel resistors. We have 1.21 amps coming from this branch. All right. And then we have 1.94 amps going this way. So 0.73 plus 1.21 gives us 1.94. KCL is satisfied at this node, and it's satisfied at every node. So KCL is satisfied. Now let's check KVL. Okay. So KVL, remember, says across any closed loop, the sum of the voltage rises and drops has to be equal to 0. Okay. So I think it's helpful to, like I said, designate a 0 volt spot and then just go through and check. So we start off at this bottom left corner. We go up and we get plus 16 volts, okay, because we're going into the minus and leaving from the plus. This gives us plus 16 volts. Minus 3.88 volts gives us 12.12 volts. Minus 7.3 gives us 4.82 volts. Minus this 4.82 volts gives us 0, and then we're back at the beginning. Okay, so that's first loop, satisfied. Okay. Let's start from this bottom left corner again. Again, we go up 16 volts, minus 3.88 volts, minus 7.3 volts. Okay, now we're here, we have 4.82 volts. Let's go this way. Okay, we get another minus 4.82 volts. Here we're at 0 volts. This one's also satisfied. Okay. Now let's go around this outer loop maybe. Okay, so let's start here. Plus 16 volts, minus 3.88, minus 7.26, minus 4.84. That'll give us 0 volts. And now we're back here at 0 volts, 0 volts, 0 volts. Outer loop is satisfied. Okay. Let's see. Let's do, well, there's a couple of other loops here. And this is something we haven't really talked about yet, so this is a good time to talk about it. So here we have a little loop. Okay? So what we can do is we can start here. We can start here at this 0 volt branch, and we can say, okay, let's go across this left. Now, since we're going into the minus on this resistor, this is plus 4.82 volts. Then we have minus 4.82 volts. Okay, so that's satisfied. And if we go the other way, same thing. We're going into the minus port, so we have a voltage rise of 4.82 volts and a voltage drop of 4.82 volts. Okay, so it's satisfied going that direction as well. Let's try something even more complicated. So, let's start from here. Then let's go up here, and we have a rise of 4.82 volts. a rise of 7.3 volts, so now we're at 12.2 volts, and we drop 7.26, drop 4.84, and we're back to 0. Okay, so KVL is satisfied here. And the thing is, if you go across any of these closed loops, okay, any closed loop in this circuit, what you're going to find is that the sum of the voltage rises is equal to the sum of the voltage drops across any closed loop, because that's just the way it has to be in order for the circuit to be solved. Okay, and there might be a couple of places in here where it's not exactly equal to 0, and like I said, that's due to the rounding errors. If you carried all these calculations out exactly, then yeah, you would get 0 across any closed loop. And like I said, this is something that just has to be in order for it to be solved. Okay, because you can't just create potential out of thin air. There has to be either a source or a drop, and it has to be path independent. That's why we say it's across any closed loop, not just any certain closed loop. So because of that, KVL is satisfied, and we solve this circuit. Okay, so here, I'm going to zoom in on this circuit, and you can see how complicated this is. I mean, this thing has 1, 2, 3, 4, 5, 6 different resistors. Okay, has 6 different resistors. That means 6 different voltage drops. It has 1, 2, 3, 4 branches. It's a pretty complicated circuit. Okay, and the thing is, there's even more complicated circuits out there, and that's something that you're going to have to tackle at some point. Okay, but the lesson is, if you know series resistors and parallel resistors, you can simplify any circuit. You can simplify any circuit into where it is just a single resistor, calculate the current, and you can just progressively find out more and more and more about the circuit until it's completely solved. Okay, and the only thing is you just have to be careful that you're always satisfying KVL and KCL, and that you're not doing anything that you're not allowed to do. Okay, so I hope you enjoyed these examples. I hope they were beneficial to you. I hope that you learned something. If you have any questions, please feel free to leave them in the comment section below. But other than that, thank you for watching, and I hope that you come back to the channel at some point.